Hello, my name is Gaehun Jo, and I'd like to share with you some of the results of our wafer-level vacuum sealing approach for packaging of silicon photonic MEMS. Let me start with the introduction part. Today, there are established, commercial, highly advanced silicon photonic foundry platforms like IMAX ISI PP50G silicon photonic platform. They provide passive submicron silicon waveguides, modulators, and germanium photodiodes with 2 layers of metals and fiber interface. The commercial foundry platforms provide access to a broad catalog of high-performance standardized library components. For example, they provide low-loss waveguides as well as many passive and active photonic components. The available foundry platforms enable dense integration, high volume production, reliable performance with reasonable cost. This is the reason the field of silicon photonics has evolved rapidly over the past decades. Recently, various novel silicon photonic MEMS applications are developed, researched, and introduced to the photonic community. MEMS in photonics have many advantages. They have strong mechanical tuning effect, very low power operation, and offer a lot of functionality such as mechanical latching for non-volatile operation. For example, there are MEMS phase shifter and single-pole double-through optical switch, and many other novel devices. Combining the capability of standard foundry platforms with novel photonic MEMS devices offers tremendous potential for improving functionality and performance of future photonic devices. There are many ongoing research efforts to make this reality. But until now, these novel devices only work in lab environments. To become reliable and fully functional long-life commercial products, the devices have to be protected. Our approach starts from here. To enable long-term reliability and functionality, we propose a hermetic vacuum packaging technology for integrated photonic devices. And this technology should work on wafer level and also need to be compatible with standard foundry platforms to enable the future commercialization of these devices. From here, I will introduce our wafer-level packaging approach, which can protect the photonic devices in vacuum atmosphere and fully compatible with the standard silicon photonic foundry platforms. Our approach is transferring 30 micrometer thin silicon sealing caps to foundry device wafer. The thin sealing caps are patterned and fabricated in the device layer of an SOI wafer. The sealing caps consist of a flat silicon lid section with a protruding sealing ring, and it is covered by thin gold layer. Sealing rings are located along the perimeter of the caps. On the ISI PP50G silicon photonic device wafer, we designed aluminum rings which is corresponding with sealing ring to enclose each photonic MEMS device in the cavity. Before demonstrating our approach on the photonic foundry wafer, we investigated the influence of the gold-coated sealing ring width and cap dimension on the resulting sealing yield. Different sealing ring widths from 3 to 27 micrometer were investigated. At the same time, 3 different dimensions of cavities were investigated to verify our packaging method. The caps with dimensions of 300 by 300 micrometer and 1500 by 1500 micrometer are designed to test a single cavity. And the caps with the dimension of 3000 by 3000 micrometer are designed to test multiple cavities. Encapsulating multiple devices by a single sealing cap can give benefit of reducing sealing footprint. For evaluating the wafer scale sealing yield, which is shown in the figure A and B, a total of 432 silicon sealing caps were fabricated on a 4-inch wafer. As shown in the figure B, after transfer bonding, the thin silicon sealing caps with different sealing ring widths had an excellent yield of above 98%, except for the 3 micrometer ring width. It is because these two thin sealing rings do not provide sufficient bond strength as a result of the small bonding area. The figure D shows cap deflections measurement of two different dimensions of sealing caps by white light interferometry. Due to the pressure difference between the vacuum inside of the package and atmospheric pressure outside, the thin caps deflected toward the inside of the cavity. And the figure C shows cap deflection over a period of 62 days. You can see there is no significant change in each cap deflection, which indicates maintained presence of vacuum inside the sealing cavities. And the results show that our approach can be demonstrated on the real silicon photonic foundry wafer. Now, let me talk about our demonstration of the vacuum packaging on silicon photonic foundry wafer. We demonstrate wafer-level vacuum packaging on the IMAX state-of-the-art ISI PP50G silicon photonic wafer. This is the cross-section of ISI PP50G and the devices that the platform can be fabricated. In these designs, we add aluminum rings along the opening, which is opened down to the waveguide level. As briefly introduced the concept of transferring sealing caps before, you can see aluminum rings which needed to be matched with sealing rings are on the foundry wafer. These aluminum rings are defined in the standard bond pad material and can be fabricated within the standard ISI PP50G foundry platform process. After opening the cavities from foundry platform, a VHF etching process was used to selectively remove the oxide underneath the MEMS devices. The result is a state-of-the-art photonic integrated circuit that seamlessly combines conventional non-mechanical photonics with novel photonic MEMS, as shown in the figure. For the vacuum packaging of ISI PP50G foundry wafer, our approach is transfer bonding of thin silicon caps. The SY cap wafer, which contains many sealing caps, is aligned to the photonic foundry wafer, and subsequently bonded inside a vacuum chamber to seal a vacuum inside the cavity. Next, the handle layer of the SY cap wafer is removed, leaving only the individual thin sealing caps on top of all the photonic devices, as shown in the figure. The narrow sealing ring is designed to have a small sealing footprint and induce plastic deformation at the gold-aluminum interface due to high local pressure during the thermal compression bonding process. Additionally, the induced plastic deformation makes the transfer bonding process relatively insensitive to the roughness of aluminum and gold contact interface, which simplifies fabrication and greatly improves reliability. To demonstrate the feasibility of the proposed wafer-level vacuum packaging, a SOI sealing cap wafer contains 30 micrometer thick caps with different dimensions, roughly from 300 micrometer up to 3 by 3 millimeter. These figures shows examples of different photonic devices using different shapes and dimension of the sealing caps. The figure A and B were designed to demonstrate sealing of the single device, and the figure from C to F were designed to demonstrate multiple photonic devices in the same process step. This flexibility to adapt the sealing cap shape to each type of device allows for a small packaging footprint and thus increased integration density and reduced system cost. In this figure, you can see a side-by-side comparison of unsealed and sealed cap. The aluminum bond rings were designed to encapsulate only the photonic devices. Additionally, the metal bond pads and grating couplers are located outside the sealing area. Therefore, the electrical and optical input and output connections remains easily accessible for on-chip testing and chip integration. You'll now understand our wafer-level vacuum sealing caps have a small footprint and flexible design which can increase the integration density of sealed devices. However, optical losses are also crucial for photonic circuits, and the sealing should not limit its functionality. In order to verify optical integrity, we also looked at the impact of our packaging method on the optical performance of a test device. On the left, you can see the device we used, which is a Mach Zehnder interferometer underneath a sealing cap. In the short arm, we also included a suspended waveguide section. After sealing, we could access the device optically with grating couplers just outside of the cap. On the right, we showed the measured transmission spectrum from 1460 to 1580 nanometer. The maximum transmission of the device follows the transmission of a grating to grating reference, which is measured outside of the cap. It confirms that the sealing does not noticeably affect the losses of waveguides that goes through underneath of the cap. Moreover, the interference fringes shows that both arms of the interferometer transmit the light, which implies that the sealing did not collapse or affect the suspended waveguide section either. To conclude, we present a wafer-level vacuum packaging approach for sealing photonic devices on ISI PP50G silicon photonic foundry wafer. The proposed wafer-level sealing did not have any noticeable impact on the standard electrical and optical interfaces, and we did not observe a drop in optical transmission for devices underneath the ceiling caps. We believe that our approach for wafer-level vacuum packaging is a significant step toward commercialization of silicon photonics, optomechanics, and photonic MEMS. I would like to thank you for your listening, and thanks to MORPHIC and the other EU project team. I am looking forward to receiving your questions. Thank you.